So recording has been started. Yeah, it is showing. Just I am allowing you to. Yeah, it is showing. Record. Okay, so let us start. So where did we stop yesterday? So we actually discussed about a very naive way of classifying, which you can think at as a predecessor of coordinates or convolution operation, that is classification by matching filters, right? So classification by matching filters, what it does is that you have filters or windows that are like typical for or specific for finding that pattern. So if you want to find a pattern like 7, you create a filter like this and you slide this filter over all the test images, and you somehow measure what is the response of this filter for sliding the filter over the test images. And one simple way of measuring that response, we found that, okay, it's a weird sort of window. So you just place it over the image in a sliding position, and whatever you can see through these white regions, you sum all those pixel values, and that sum is your response. It's a measure of your response. So for you do this, all these things, that is getting the response for this the operation of sliding this filter over all these images, and for all these images, or take it in basically other way around. So for this image, if you don't know what is the level, you slide all these filters or windows over this image, and the response that is giving the maximum, that is the filter that is giving the maximum response for this test image, that you classify, that is the image you classify as that filter. So this is the filter for 7, this is the filter for 5. So if it so happens that for this image, sliding this filter gives the highest response compared to this or this, then this is a 7. That is the idea. That was a very naive idea of classification by matching filters. But we said that what if the test image is a little rotated, skewed, or zoomed out? Because I mean, you see that this filter looks very much like this 5. Actually, when I prepared that filter, I prepared from this image only. So it will give very perfect response. That is, this filter will give very perfect response on these, and like very low responses on these images, right? So, but it may not always be the case. I mean, what if the 5 does not look like this? Maybe it looks like this. Then what will happen? Will this be giving you a good, better response, or maybe this will give, or this will give? It can happen, right? Or even it is a little rotated. I mean, though I have prepared this 5 from this 5, if I get a 5 which is just a rotated version of this, then what will happen? Will this filter give the requisite response? Or skewed, that is a stretched out version, or zoomed out, what will happen? I mean, it is not even the same size of this filter. This image is not even the same size of this filter. What will happen? So that those questions can come, right? So let us see. We have actually tried to experiment with the same 7 filter. That was the same image, and for this, we will just try to see only the effect of rotation. So if we slightly rotate the same image where we were searching the same, the 7, what will happen? So earlier we found a very high score, like 18,604. But if we just slightly rotate it, 18 degrees rotation, not much, the response, the highest response, actually dramatically reduces to 9974. So, but I mean, what is more surprising is that you get a higher score than even this image, than this image in this image. That is, if you are sliding this 7 on this, you are getting 10,278. So if you compare these two images, I mean, of course, this you will give as, say, the class 7, not this. So the thing is that this is one. I mean, this is actually a one that we have taken it from one of those 6,000 or 7,000 images of one in MNIST. So actually, this can harm the performance. So we see that a simple sliding filter, this matching filter, is not very robust. It can easily break with like some natural variations like rotation, zooming out, stretching, etc. Of the images, and we many times see those variations in the image, right? So before going to see how we address such issues, I want to mention one thing. So though we are saying this operation as a sliding of the filter, it is also known as the convolution operation. Though I must say that convolution, I mean, this term has come from the signal processing community, but there the convolution is a little different. So if you have taken any signal processing course or say networks and system, I think it is called signals and systems course, in that those courses you must have come across convolution or even convolution operation in probably some mathematical maths courses also. There what you see is that your convolution filter is actually first mirrored, so it is flipped and then you slide it. But I mean, this name actually stuck with this operation. We are not mirroring it, just we are sliding. So just for say legacy reason or historical reason. Now, in signal processing community, actually this particular operation that we are doing without mirroring, that also has a name. I think that is called correlation. But again, for the purpose of the course, we will just say that, okay, this is the convolution operation. Though you just, as an aside, you must remember that convolution in signals and systems or signal processing community is a little different, just a slight difference is there. Okay, now let us go to see what we can do to address the issues that I told. So we saw that there may be many natural variations and where one single filter can break. So one naive way to address this issue is, why don't we go for a lot of such filters? So kind of encompassing all sort of variations, which considers these all possible variations. For example, we can have not only one 7, but a few such 7-like windows, right? With different rotations, different skewness of those 7s. So those windows or filters can actually encompass all the variations of 7. And then we will just test one by one all those 7s. And if it comes that, okay, instead of all those filters corresponding to say 1, some filter in these variations of 7 gives you highest response, then that's a 7, something like that. Okay, so you just increase the number of filters, but that means, I mean, your class is ultimately 10 classes. So you might think that, okay, naively I can have just 10 filters, but what it says is that, okay, for each digit you will have say 15 filters each, different skewness, different rotations, etc. Right? So believe it or not, the coordinates try to come up with such filters. So one naive question would be that, okay, how can we get those filters? I mean, what will be the amount of rotation? Even if I tell that, okay, you take say 15 different filters. So out of these 15, which say 5 will go for different rotations, which 5 for different skewness and so on. So how can you know? So that's why this learning, the term learning comes, right? So in coordinates, you learn those filters. And that's a very naive way to think about the coordinates, that it tries to learn different filters corresponding to different patterns, not only 7. So it can be some simple vertical line. So if you want to, so there is say image, and you want to basically detect whether there is a vertical line. So you can actually have a filter where everything else is 0, just there are 1 here, right? And you slide it through this way, this way, this way, and wherever this response is highest, you say that there is a vertical line. Now, here I cleverly told 2 things. One is that the size is sort of 3 × 3. It is not even same as the size of the image. So that is one thing, and we will shortly see what is the advantage. But what we have earlier seen is that the size of the filter is same as the size of the image, but always the images may not be of same sizes. Different test images may not be of same size. So that is one thing how to deal with, and or one reason why we do this sort filter size. Another or many other reasons are there. One is that okay, you are trying to basically decompose a complicated say shape, suppose a dog, into different basically ages. So I mean, a dog might look like this, this. Okay, so these sort of, I mean, each of these can be different filter that you are looking in the image, and when you compose it, then it might give a dog-like shape, right? So the way to compose is basically to use different layers. So you combine all this. Compose is just a fancy name for combine. So you combine these filters and get. So again, I'm giving a very much overview of this. These are all, it will come when we visualize some of the filters at the end of the this topic. But yeah, I mean, these still are like, it works good. So we are trying to come up with justifications. We are trying to, I mean, in research, you will see that you try to, maybe if you are trying to go for say, per se, artificial intelligence. So what is not artificial, you try to mimic them, right? So whether a human does in this way, whether what happens inside human brain, if we can mimic. And actually, again, I will not go into much detail, and I don't know about neuroscience, but people have looked into it and said, I mean, have seen that, I mean, the neuroscientists have seen that in humans, visual cortex, actually some sort of those, I mean, there are neurons which fires for different ages. It's not that always you try to look for a complicated shape at the very beginning. So the initial part of the neuronal systems in your visual cortex, they fire for ages. So those things will come. I mean, for the convolutional neural network, not for the I mean, the neuroscience literature. But when first people thought about these coordinates, I mean, they took inspiration from them. And I think in the very first lecture, I told about Professor James DiCarlo at MIT. So if you go into that talk, or even look into some of the papers by their group, you will see those sort of findings that they're trying to come up with. And actually, it is not only that, okay, you take inspiration from the from human intelligence to artificial intelligence. The other way around also they are trying to do. Anyway, so just aside. So yeah, so that is one of the reasons, like the human motivation, the size of the image can be varying. So you can actually take this. I mean, you cannot probably know at the beginning what is the size of the filter that you need to take, if you have to take it as the same size of the image. Now, there is another reason which I will come. So before that, just let me give a little overview of this figure. So the input is an image, which is here called input data. In this particular slide, it is a grayscale image, and you know now about what is the difference between grayscale image and color image. In color image, you have 3 channels, right? So there is like this volume. So you have 3 2D arrays, sort of, right? But I mean, for the purpose of this slide, I mean, we are just going ahead with grayscale image. And what this gives, what is one such I would say 2D array. So there are say how many, I don't know, I have not counted, but maybe there are like 16 such 2D arrays. So what does this one 2D array give? So if you now try to slide this short filter over the image, what will happen? So let's say this is the whole image. This was the short filter. So this was, say, the 3 by 3. So you just place it on the left top when you coincide the left top of the image and the left top of the filter. You get this multiplication of these element-wise multiplication of these values. Why I'm telling element-wise multiplication? Let me go with one of the previous slides. So I forgot to basically draw that connection. So how can I? Yeah. Okay. So where it? Yeah, this. So you see, this is the example from that MNIST image, and this is the window. So you see, these are these are 1, 1, 1, right? So when you place this filter over, say, this image, right, you are, say, getting something like this. Okay. Oh, this color is okay. Oh, you are getting something like this, that this is the portion that you see, and this has some intensity values, that those we were summing. So that I explained yesterday. So suppose this was this part, I don't know, but maybe this part was being visible in this slide, in this basically portion. So suppose this was just getting overlapped with this. So this was the portion that you see of this image, and you were summing it. But you can think that, okay, this was the portion I was seeing, as I said, this was the portion, and this is the portion through which in the filter I was seeing. So you can take this operation, that summing the intensities here, by another operation, which is element-wise multiplication of this value 1 with the corresponding overlap value, say this 21, this value, this one, with the corresponding value, say this 214, and so on. So you element, so I hope this is clear what I mean by element-wise multiplication. So if your filter value at a position is, say, W, say W1, say Wij, the ith row, jth column. Okay, and your the value that you see through that Wij, that is the value, intensity value of the actual image in that position, is, say, 21, or say it is Xij, right? So you are doing this Xij and Wij, and for all Ij, for I is equal to 1 to 3 and j is equal to 1 to 3, right? Because it is a 3 by 3 window, and then you are doing this sum. So element wise you are getting the product, and then you are summing. So that is the idea of convolution also, right? So what I want to make the point is that if you want to take the sum of the elements here, what you see of the image, you can equivalently think it as element wise multiplying the filter value with the corresponding intensity value of the image, and then sum, right? So that will give us a more generic operation that we do in convolution. So let us go here. So this is the okay, so that went away. So yeah, so let's say that is the operation. So you can think that if your filter value is what I said, say 0, 0, 0, 1, 1, 1, and 0, 0, 0, then you are element wise multiplying with these values, that is these values, with the corresponding intensities and taking sum. That sum is a single scalar. So you are, say, putting it somewhere here. Now you slide this window to another position. Say just you slide it towards right by one single pixel. So this is now the position, right? So you get another, if you do the element wise multiplication and sum, you get another value, right? So it is just a single scalar value. In this way, you will get some values, and you will also slide it below. When you are done with this part, say, when you are done, then you will come here, right? You will come here. So you will put this value there and so on. So this way, you will also get as a response an array of 2D array of values. It's not just a single response as we were getting if the filter was of the same size as the image. right? So you will get a 2D array, and this is the 2D array. So for a particular filter, when you slide like this on the image, you get this 2D array. For the second filter, which is say 0, 0, 0, 1, 1, 1, 0, 0, 0. In that case, you get say this filter, the second one, right? Sorry, this response. In DL terms, deep learning terms, these are called feature maps. So this is one feature map. This is another feature map. In this way, let's say there are n feature maps, or say 16 feature maps, whatever. So that means you have these number of filters here that you operate separately on the image, and you get these separate filter maps. Sometimes these are called, not sometimes, in many times, these are called number of output channels. So you know about what is channel in a image, right? So you have RGB, right? 3 channels. For a grayscale, just one single channel. So it is not that 3 or 1, it can be as many. I mean, when you get the responses, it can be as many responses, or as many channels, or as many 2D arrays as many you have the number of filters. So if you have 64 filters, you will have 64 such number of channels, output channels. So input channel. So if I am saying output channel, what is an input channel? Input channel is the number of channels in the input to the convolution operation, and output channel is the number of channels after you have done your convolution operation, right? So this is the convolution operation. We will come and visualize more on what are the values, what will be the size of these 2D arrays, those things. I'll just wait for 1 or 2 more slides. I'll come. And then we have this pooling operation. So generally, after that, we have some activations. I am not sorry, yeah, the activation functions. One thing I cleverly, I think, told it about. I mean, I'm not going back in there, but it was like the Wij Xij sum. This thing I wrote, right, over all I and j, right? Now this should remind you to the similar type of operation that we did in simple ANN, not the connet. That is the WX plus B. You can also have a bias term here. I'm not, just for the simplicity, not showing the bias term. That is Wij Xij plus B, right? So this is the linear operation. Convolution is a linear operation because only you are doing this WX plus B. Here B is 0, 6. So then what we did in case of artificial neural networks, the simple fully connected neural networks, we passed it through a nonlinear activation. So you can actually pass it through basically the ReLU or sigmoid, etc., whatever is your choice of activation function, right? Then there is an additional operation that we do, that is called pooling. What is pooling? Generally, I mean, there are different types of pooling, but the idea of pooling is basically to reduce the size. Because you see, from one image where you have, say, 3 channels, suppose the image size is 100 by 100. So you had to store like 3 into 100 by 100, so 30,000 values, right? So, but here it can be, say, not 100 by 100, suppose it is, say, 98 by 98, or whatever, right? These value. I mean, we will see it will be a little bit reduced because we cannot slide all the way for all the rows. So what will be the exact size of these 2D arrays? I will come, but it's very close to, say, 100 by 100. In that case, the number of numbers that you need to store in the computer, so that you need to store these activation values, because you have to do back propagation, or even you have to get ultimately these prediction values, right? So you have to store 100 times 100 times, say, 16, if 16 is the number of filters. So this has increased. So there should be some way to basically reduce this storage requirement, right? Or the computation also. I mean, if this size is so big, again 100 by 100, again if you do convolution on this, you have to slide it so many times, these many times, right? So that you need to reduce. So because to basically reduce that, And to get another thing which is called basically, I think it is called shift invariance that will come, we generally employ pooling. So what is pooling first? Let us see. So pooling is basically you divide this whole image. Let me actually discard this. Yeah, so you divide this image into, say, some patches. So suppose 2 cross 2 is your patch. So you take a 2 cross 2 portion. There are 4 values of peak intensity values, or not, are not intensity value. What did I say? It is called activation map or feature map. So the activation values that you have. So we have seen the term activation earlier on artificial neural network, right? So after the basically doing the linear operation, and then the what is that the activation function, passing it through the activation function, we get the activation value. So you think similarly that you have an activation value. So because that is the same thing that you are doing, linear operation, then passing it through activation function. So you get this 2 by 2, that is 4 values. You can take, say, the average of these values. That is called average pooling, and put it here. Now again you take another 2 by 2 window just by the side of it. You get 4 values. You take the average of it. You similarly you place the window here. You get there and so on, right? Single value. Similarly here. But so again, I mean, you are getting a 2D array of values as an output of the pooling operation. But the size is now reduced. Why? Because I am not deliberately overlapping. So I am not taking a window like this. I have taken, if I have taken this, I am taking this, then this. I am not overlapping. So at least it will be reduced to half, right? Sorry. So so that way you get the reduced size. And generally in pooling operation, there is no overlapping of the windows, and the number of channels, they don't get reduced. Basically, you do it channel wise. That is this averaging operation. You do it channel wise. That is, you to do the averaging operation on this channel separately, you get, say, this channel. You do this on this channel separately, you get this channel, and so on, right? So this is one way. It is called average pooling. Another is max pooling. So you can take only the maximum of those 4. There are advantages of doing max pooling that will come. And then there are other ways of pooling, like Gaussian pooling, etc., etc. But mostly 90% of the cases you will use max pooling. You will see. Then again, you can repeat these operations. That is convolution, activation function passing, then pooling, and so on. And after you do it, at the end, what you do is you something called linearize, or not linearize, vectorize this output. So this is, say, the feature map. So it is called C1 feature map. That is the first operation, or the first layer is S2, C3, 4, etc. I mean, these naming conventions will go away later, and there will be better naming conventions. Just you think that this is the last pooling operation that you have done. So suppose you have got a feature map of dimension. The 2D dimension is, say, 7 cross 7. That is this is 7 and this is 7, right? This and this, right? And you have, say, got, say, 100 such filter, right? Say 100 filters. So you have got, say, 7 times 7 times 100, that is 4900 values, right? So what you do is you just put them in a long vector, not this 2D array, just a single 1D array where you have all these 4900 values. Now, so I should have probably drawn it in a rectangular, vertical form. That would give you more familiar looking pictures. So these are the 4900, say, numbers. Now, suppose you are actually trying to learn a classifier which can classify among these, say, these 3 classes, say the human face, a dog, and say room. So you will have ultimately these 3 nodes, and you connect it through this via this fully connected architecture, right? So you do this. So that is your fully connected layer. It generally is called fully connected layer. This is called convolution layer. This is called pooling layer, and so on. I mean, sometimes it is also called the linear classifier, the fully connected layer. And that this is very much same as the ANN. So I'm not going into detail with it. So again, just to summarize the ConvNet, the overview of the ConvNet. I mean, this is the generic form. We will come into different architecture starting hopefully tomorrow. So you have input data, you perform some convolution operation, you do some pooling, I mean, pass it through activation function, then do pooling, con, pool, I mean, con, activation, pooling, con, pool. So activation function, we generally don't even tell it. It is so much trivial that, okay, after linear operation or the convolution operation, you will do the passing through the activation function. So con, pool, con, pool, con, pool, this goes on, and finally you have a linear classifier or the fully connected layer to get the final predicted values. I mean, you of course add a softmax there, right, to so that it gives you the probability values for the number of, if there are n number of classes, then the n classes, right? So this is the overview of basically the ConvNet. So I shall actually go into small, slightly other things, pooling and this, and then I will stop. So because I think some questions may arise, but some questions may also, I mean, you can get the answer from here also. So one advantage of doing that sort of smaller filters, not even the same size of the image, that I said I will come later. So one of them is this. Say this image is 100 by 100. Suppose this is 100 and this is 100. So you have you remember the expression that Wij Xij that I was doing. So if you have a filter which is again the 100 by 100, that is the same size of the image, then what will happen is that you can think of it as okay. One thing I forgot to mention. So before I forget, let us go. So these filters that I have shown here, these may not always just contain these values 0 and 1. So I was probably drawing it like this for a vertical edge, like 1 1 1 0 0 0 0 0 0. It may not always contain these 0 and 1 values, right? So you can basically I mean that is the idea of the training of the ConvNets. I mean, it can be 5 7 8 9.2 minus 0.2 and so on, right? So it is just any real number, and that you will learn. So whatever helps you to classify the image, U means the ConvNet, the convolutional neural network, it will learn. So it will learn these weights, because what will you learn if you give this 0 1 0 everywhere, or like if you just predefine these filters, all these filters, as I said, there are 16 filters, so you get 16 output channels of the feature map. So if all these 16 filters, you just give the values 0 0 1 0 1 0 whatever, that is for first one, second one is this, and so on, then what will you learn ultimately? So these are the weights that you will learn, and this can very well have such values that I gave here, right? So and that is the idea means that will help. I mean, these learned weights will help to classify it in these classes, right? So the basic idea is that, okay, I mean, you will learn these weights. So this Wij you will learn. X is the input. So now come back to the scenario where we were discussing about that the same size of the filter. So or the filter is of the same size as image. Then this operation you can think as you are just vectorizing the whole image, that is the 10,000 values you are having. So 100 by 100 means 10,000. And you also have 10,000 weights, because it is the same size of the image. So you have this, and then you are basically kind of getting these connections, right? And this you are then all these weights you are learning. right? So you have to write sort of 10,000 values. Instead, what you are doing here, you are only learning 9 values, and you can think of it as the same 9 values you are sliding, not just, I mean, instead of 9, say I'm drawing 4. The same 9 values, if that is like 1, if it is 0, if it is 0.5, it is negative 0.2, the same 4 values are you are multiplying with here when you are sliding it down. So you are getting ultimately the values, that is one scalar for this operation, one scalar for this operation, but you are actually reducing the number of parameters. So I know, I mean, this you need to just think about, and but try to draw this connection to the fully connected layer. So you are actually reducing the number of, if anything does not convince you, this operation, you think that, okay, if the same size of the image I am taking as that of the filter, or rather the opposite, if I am taking the filter as the same size of the image, you are basically learning these 10,000 values, which you are not learning in case of a smaller size filter. There are many advantages. One is that, okay, the composition that I told, and then which is human-like, so to say. Then another is storage and computation efficiency. Another is this shared computation. I mean, this is also called shared because you are sharing these weights for all these 4 what is called quadrates, quadruplets, whatever. So basically for all these all possible, not all possible, these consecutive 4 nodes. So that is one advantage for the smaller size of the filters and shared weights. Now pooling. So I said that pooling has this shift invariance. What does it mean? Is that by pooling, for example, max or average filter ratio, we gain robustness to the exact spatial location of the feature. Suppose this is the image, and you are trying to say find an eyebrow filter. Okay, so these Einstein's images say eyebrow is here, and when you have this filter, when you are say at this position, like this. No, I think I'm wrong. How can I? Okay. Yeah. So yeah. So this square filter, this one, something like this. It is very hard to, probably an interactive class would have been good in that case. But yeah. So here, suppose you have at a certain image of Einstein, you get the eyebrow is there somewhere here, right? So then you are getting this basically activation value after doing the conv operation for the next slide, that is the next position of the filter, probably this. Yeah, you are getting this value, and that's the third one, that is this one, you are getting this, and similarly for the vertical ones. Now when you do a pooling operation over a 3x3 window, you are getting this value. Now if the eyebrow happens to be slightly shifted in another image, suppose somewhere here, right, the left eyebrow, so the response for that eyebrow filter will be maybe some, I mean, it was previously highest on here, it is now highest here, right? So when you do the pooling, ultimately this 3x3 window will give you the same response. But if this pooling operation was not there, maybe in some image it was there, the highest response, in some image the response was there. So it might cause confusion to the later layers, because after this, I mean, you will have other values from the next 3x3 also, right? So this is coming from here, the pooled value, and so on, right? So after you do this, then you will again do conv and so on. But now it is slightly different. I mean, if you don't do this pooling, if you try to do this, then the 3x3, which was giving highest response here, the 3x3 filter after this, which was giving highest response here, will now give say highest response there, and so it can give confused, it get confused while learning. But here you are at least taking care of slight perturbations. So again, this is again a high level view of trying to justify why pooling helps. but at least intuitively that if you have slight change of the position of the input, the response will not change ultimately, right? So you don't want that, okay, if the eyebrow position is somewhere here now, this should not, you don't want that this should not be classified as a Einstein image, sort of, so to say, right? Okay, so before I go to a more, I'd say visual treatise of convolution, what is the size, etc. If there are questions, please ask. I see one raised hand. Let me just go back to there. Rishabh, okay, I have asked you to unmute. Yeah.
Sir, am I audible? Hello?
Yeah.
Sir, in this case, you said if the eyebrow is slightly shifted, the max pulling will help. But sir, like if it is inverted, then max pulling won't help.
No, inverted means a lot of. Sorry.
If the same image, the Einstein image is inverted, and then we tend to.
By inverted you mean flipped, like mirrored?
Yes. No.
Yeah.
I mean head down.
Yeah, head down, right? Yeah, so that is like vertical flipping. No, that will not help because pulling only helps slight perturbation, because that might mean that, okay, the eyebrow actually went here, right? So that is not taken care of by pulling. So in that case, what you have to tell that, okay, this is also an image of Einstein, the flipped one is also an image of Einstein to the model, and it will try to figure it out, right? Okay. So it is just slight perturbation that will be taken care of by pulling. Yeah. Any other questions from anybody? I think Rishabh, there is another Rishabh. I think I am not getting the full name. Yeah, I'm asking you to unmute.
Yeah, so we are using the pulling method to capture the local features of the image. Now
that is one of the not local features, sort of the variation. It is as I said, gain robustness to the exact spatial location of the features, right? So gain robustness to slight perturbation. That is one of the reason to use pulling. Other reasons I have told, like reduce the computation, reduce the storage, etc. Okay, yeah.
So we are capturing the pulling through a mathematical object called matrix, where we have values inside it. Now, how do we suitably select those values?
Yeah, actually, I am probably getting your question. You are saying like, there is a mathematical operation, but there is no learnable part here in pulling. So we'll come to that. But if your question specifically is like how or what is the size of pulling, whether to take average max pulling, is it the question? I'll ask you to unmute again. Yeah.
Yes, I was just wondering that how do we select that pulling values inside that particular matrix, so that while applying it in the image, I get the the robustness that I'm expecting.
Yeah. So the rule for max pulling is that this is the whole image, right? Now, this is say how many, whatever may be the size of it. You take a say 2x2 window. Now this, whether you take 2x2 or 3x3 or 4x4, that has to come from your design choice and maybe from some expertise which works well, which people have found to work well, or you have to just try with different. So that's a separate thing, like whether you take 2x2 or 4x4 or anything. But let's say we go ahead with 2x2. Then this has some intensity values, say 1, 5, 8, 92. This is say 51, this is 82, and so on, right? So in this 2x2 window, you, for max pulling, you take the value that is maximum. So out of them, say 1, 5, I think I have taken 51 and 82 or whatever. This 82 is the highest. So the output of pulling operation, when you give the pulled or the pulling window here, that is the first top 4 values, then the output is 82. For this thing, maybe it is say this is 101, so it will be 101, and so on, right? So that way it basically goes on, right? So you don't have a W value for a pulling window. It's just a window. Okay, I hope this answers your question. Oh, you don't unmute when you are asking the question. Yes, that meant, yeah. So I have asked you to unmute.
Yes, yes, sir. Yes, sir.
Okay, okay. We will look into the visualization of it. We are coming there.
Okay, that means we are sort of.
Sorry, I mistakenly unmuted. Sorry, muted. Yeah.
So we are sort of pulling out the maximum intensities from the image.
Not from the image, from that short window.
From the sort of window.
Yeah. Okay. I see again some question from Rishabh. Yeah, if you can quickly ask, that will help.
Like in this case, you said we are taking a 2x2 and taking the maximum intensity out. So like initially, like I'm applying a max pooling and I take 5x5. So I means 5x5 initially. So sir, it is a large matrix. So can it cause a loss of information, sir?
Yes, yes, yeah. That is the reason why. I mean, you might be tempted to take 5x5 so that it can handle. I would say greater perturbation, but then there will be more loss of information. That's exactly the reason. Yeah. Okay. Let us go ahead with the visualization. So Rishabh, you can lower your hand. Okay. So suppose how does this convolution happen? So let us take a closer look. So suppose this is the filter, and as I said, it can be any value other than 0, 1 even. Let's say this is the image, and you see the image is 5x5. That's the size of the image, and it's a grayscale image. The filter is 3x3. What you do, I don't know whether, let me try to, so, yeah. So yeah, so you put this filter in this first position. First position means you coincide your top left of this filter with the top left of the image, which is just shown here. The values, as I have shown as subscripts, these are the values from the filter. So 0, you see 0 here, 1, you see 1 here, and so on. And these 3, 3, 2, 0, 0, 1, these are the values of the image, right? So that way I'm just visualizing, I'm showing you that both the value of the filter and the image. Now what you will do in the very first position, it is 3 times 0 plus 3 times 1 plus 2 times 2, that is this 3 times this 0, this 3 times this 1, this 2 times this 2, and so on, right? And after you do this summation, I mean element wise product and summation, you get this value 12, right? Similarly, for the next position will start one position towards to the right. So this is the top left of the filter, or this is where you put the top left of the filter on the image, right? So now if you again do this 3 times 0, 2 times 1, 1 times 2, etc., and sum it, it is again coming as 12, and you go ahead in this way. So you get this basically third position, then vertically you come down, then here, and so on, right? So finally what you get, is this 3x3 activation map. So this is for one filter, one convolution filter. So if there was another filter like 0, 5, 8, 2, 9, minus 2, 81.5, negative 0.7, and you do the same operation, you will get another such 2D matrix. That will be your second output channel of the filter map, right? This is pretty simple. Now you see that the size has decreased from 5x5 to 3x3 because you cannot go beyond here. I mean, even if you try to put it here, this is not allowed, right? Or if you try to put it here, this is not allowed. So that is the maximum you can go. So you get 3. One for 3 is one for this and another for this. So 3 such values, and in this direction also 3, right? Now, to sometimes if you have, say, very small images like these 28x28 MNIST images, after 2-3 layers, and if you have a bigger filter size, say 5x5, the size can reduce very much, and that can hamper the basically performance. So you have to devise some way so that the size after the convolution operation actually remains the same. And there are other ways, we will come when we discuss about the architectures in detail. You can even increase the size. That is also required sometimes. So that we are not going. Now we will come later. Then another thing is that, but I said that, okay, if you don't reduce the size, computation and storage will be a big for the bigger images. So for that, pooling is there. So since pooling is actually subsampling the images or the reducing the size of the feature maps, we can actually get away of that reduction operation, the size reduction operation in this conv operation. So how do we do it? It's very simple. You just add some extra values throughout the boundary of the image. So what are the extra values? You can take anything. You can take some random values. You can take the suppose the duplicate of these values. So you take here 0, here 1, here 3, here 2, here 1, right? Those are different options. You can even take a smoothened version. Like you take these basically 2 or 3, even 3. I mean, if the image is bigger, you can take this 3 or 2, whatever number of columns, and you can do an interpolation or rather extrapolation, so to say. If it is 2, 1, 0, what will be the next value? If it is 1, 3, 1, what will be the next value? Those things you can do. But simply what works best is just adding 0, and that is called zero padding. So if you do this, that is 0 everywhere, just you can pad with 1 column or width of 1 or 2. I mean, by 2, I mean here you will have 1 more 0, here you will have 0, and so on. But let's say that is not done. So now what will you do? You will put your first position of the filter here, second is here, third is there, right? So second is here, third is there, and very simple. And then the same operation that you did in the last slide. So now what you see is that you can actually go ahead with 5 positions, because this is 1, then this, and sorry, I'm wrong. Okay, let me delete this. So this is the first position, then this position, this position, this position, and this position. Then you cannot go, because here it will again overflow. So you get 5. So you can do with convolution with 0 padding to keep the same size. Let us go into another. What is happening? Yeah, another thing, which is strides. So we have told that you can move in the previous slide, or even the previous to previous slide. You can move. After you are done with this, you are moving by 1 pixel, 1 column. Then again here, so 1 column. But you can just think that, okay, why is here? Why I have to move after I put the filter here? Why I have to move to here? I can go directly to here. So I can just take a stride of 2 pixels, not 1 pixel, right? So that is what it is done. So convolving a 5x5 input with a 3x3 kernel. Okay, that is another term. Sometimes the filter is also called kernel. So filter, kernel, window, they are all interchangeably used. So convolving a 3x3 kernel over 5x5 input using 2x2 slides. So I have taken all these images from a document by this Vincent Dumoulin. You can search in Google, you will easily get it, like convolution arithmetic or something, that was the name. Okay. Now, if you do this 2x2 stride, what will happen? You can see first position is this, second position is this. So for this first position, you get this value. For the second position, you get this value. Now you are done with this horizontal stride. So you are going to this vertical stride. And this vertical stride means you are getting this value first position, and the second position is this value, right? So you get a 2x2 output now. So that way also size reduces. But these are all the variations that I wanted to tell, right? Now, this is basically convolutions with strides and 0 padding. I'm just combining both stride, that is 1x1 stride, and 0 padding. This is just a combination of this. Still, I'm using 1x1, but I'm showing both. Okay, and this is just an I mean some extra slide. Let us basically go to this slide and we will stop there. So this is an important slide. We have kind of intelligently or cleverly not told about the channels. So or output channels we have told, but not the input channels. So you can have 3 input channels, right, for an image, which was the original input. Then you do conv, pool, etc., and you get, say, 16 output channel, right? Because suppose you had 16 3x3 filters. Then you again do conv operation, pool operation, activation operation, etc. You get, say, some size of 2D arrays, but these many filters. Say this is, say, 32 filters, and so on. So when I have said that I am doing conv operation on these 16 channels, what am I doing? Because I have these many values. So my filter was always a 2D array, it does not have a channel, right? So what I am trying to say is that here you see this was also a single channel and this filter is also a single channel. But if I have another additional channel for this image, do I need to have another additional filter channel also? The answer is yes. Okay, so that is what is shown here. You have 2 input channels. You should have then 2 filters. So what you are doing is that you are multiplying this filter with this is the corresponding color. That is the blue and whatever, this mauve color you are multiplying here. And you get, say, 2 values. So when you put this here, you will get 1 value. And when you are putting this thing over here, you will get another value here. You sum them and that will be your single value. Similarly, let me just for the time being go ahead with another color. When you are putting this filter, that is this filter here, and say this filter here, I'm not drawing it, no, just not to clutter. You are getting 2 values, this and this. You are summing and you are getting this value, and so on, right? So this is then, so this is again, this is for the first filter, first 3x3 filter. This is for the second 3x3 filter. This is for the third 3x3 filter. Now, this is important. I just ask you to pay attention here. Whenever we call it as a 3x3 filter, what it means is that it is not just 9 values. It is 3x3 cross number of input channel. Okay, number of input channel. So there are 2 input channels. So you have 3x3x2. But it is so trivial and so implicit that people just call 3x3. Because people will basically think that, okay, you will tell or you will get the idea that it is actually 3x3 cross number of input channel, right? CI, I think it is called. Later we will see. C input, that is channel underscore input. And you have, say, 3 such filters, so that you ultimately have 3 output channel, right? CO, whatever. So I'm just stopping here. If there is any question on this part, I'm stopping the lecture here even. We'll go ahead with a few more slides that are staying, remaining 2 more. Any questions on what is the input channels concept, what is output channel, or any other thing on this lecture? Yeah, I think there are so many hands. So Rishabh, yeah, I'm asking you to unmute.
Yeah, so I just had a basic doubt. I mean, the first image that we have, what does this 2 layer mean? I mean,
yeah, this you are saying, right?
Yeah.
So you see there are 3 channels, or you know that there are 3 channels in colored images, RGB, right?
Yes, sir.
Yeah, so instead of 3, I am just showing 2. That's it. One thing is that, but you can extend this idea to this. Let me go to one of the previous year here. You see, even if you are starting with one channel, you are getting finally here, say 16 channels, right? In the output after the first conv pool operation, right? Then you are doing again conv, right? So now you don't have only one single channel on the input. So the input to this conv operation is what? This whole thing is not so?
Yes, sir.
And the input to this conv operation was this thing only, which had only one input channel. And here you have, say, 16 input channel. So you have to deal with multiple input channels for conv, right? So this multiple input channel I am assuming here as 2. Okay, that's it. Okay, I hope this answers your question, right?
Yes, sir. Yes.
Okay. I see Deepak is asking some question. Yeah, I have asked you that, Deepak.
Sir, I have a little bit confusion in the size that you have lastly declared. The 3x3 is the 3x3 is the size of the filter.
Yes, this one 3x3. You see, 3x3.
Okay, and then multiply by number of input channels, which means two filters are there. That's why we are multiplying with 2.
Exactly. I mean, it is like if you say or if somebody says that you have 3x3 filters in a conv layer, what you have to kind of see, what is the number of input channel or what is the number of channels of the input on which this filter works. If that is, say, 5, then each filter, each 3x3 filter will have 5 such input channels also. So if you have 5 input channels for the input, each of these 3x3 filter will have 5 such input channels. Does it make things clear?
Yes, sir.
Now, yeah, now for one such 3x3x5, I am just for the sake of clarity, I am saying that it is 3x3x5, but it is actually told that it is a 3x3 filter, right? So for one such 3x3 x5 filter, you get one 2D array as output, which is also of size 3x3, right? Is that clear? I mean, I'm just asking you to unmute. Right?
Yes, sir.
Right?
Yes,
so, sir. Yeah. So for a second 3x3x5 filter, which is this, you will have another 2D array, whose size is some 3x3 again, right?
Yes, sir.
And for the third one also you will get. So there are 3 3x3x5 filter, right? 1, 2, 3, and for them you get your output features, and these 3 are the channels of the output feature map or channels of the feature map output. So this is called that, sir. Okay, you have 3 output channels. So you have 2 input channels and 3 output channels here. So because of 2 input channel, each of the filter will have 2 input channels, and because of 3 output channels, there will be 3 filters. Does it make things clear?
Yes, sir.
Good. Okay. We'll come back to this thing tomorrow when we will do a bit of like what will be the size of the output, etc. Those things. Yeah. Okay. Sagar, I think I can just give you the chance to ask, but before that, I have some logistics related questions to take. So I am actually allowing you to unmute yourself. So if you have any questions about the presentation, the first set of presentation is going to happen in this Tuesday. So if you have any questions, please ask. Okay. I mean, you can unmute yourselves now.
Hello, sir.
Yeah, yeah.
Like as I saw the Google sheet, the sheet, I saw the topics were given by you. So is it that you will give the topics or?
Yes. It is just one paper for the semester. So I'll just like encourage you to read the paper that I am giving to you. Okay. And I think the mail has not been sent by the student volunteers for you guys to send them the slide. They will in turn send me the slides, which I will again upload to the course website. So, but they will probably send it sometimes on Friday so that you remember, and you have to send it to me on Sunday. Now, the thing is that the 5 groups that are presenting this Tuesday, they will send it this Sunday. The next 5 group, they that are presenting on the next Tuesday, they will send it just the Sunday before that. So I hope this part is clear. Not that it is not that everybody needs to send their slides this Sunday, because I will choose, and I have chosen things that are sort of related to what has been covered or what is being covered. Though I am running 1 class late, but still it should get you started. Okay, so after these 15 papers, after these convenient architectures, I will discuss about detection segmentation. So next group of say 15 or 10 whatever papers, it will come related to that, and so on. So that is why I am telling that, okay, you don't have to send the slides right now if suppose you are given a detection paper to present, because that will be a little hard for you guys to understand. But again, this is a one-time task, so I am deliberately giving something that you will not get all from the course. I mean, that is the idea of a high-level graduate level course, right? You have to work on your own also. Okay. Any other questions on presentation? And you can unmute yourselves.
Apart from the, this will be in the office hours, right, sir?
Yeah, this will be in the office hours, Tuesday 6 p.m. Yeah,
and every members which are not on the group can also attend.
Yeah, I will encourage. I'm just not forcing you guys, because that is outside the class. Okay, but I think if you and that's the idea why I gave the papers earlier, that you will take a look at the paper. Maybe the title itself is interesting, and you want to say know about the paper. So you just come, because you don't have to read the paper. You just listen to it for 10 minutes and you will get the brief idea about it, right? So you don't have to read the paper, but you will know about the paper at least, what it does and so on. Now, if you are interested more, you can go and explore more. So that is the idea, right? Any other questions? I see Deepak, you have raised hand. Any other idea? Sorry, any other question?